In the previous presentation, we discussed about the photoelectric effect, and I stated that photoelectric effect was one of the most fundamental experiments that showed us that the electromagnetic radiation that we are talking about is not just a wave, but in some of the experiments, our electromagnetic radiation can be treated as a collection of quanta, what we call as a photon. Now, this Compton effect is also explained using the particle behavior of light. In this experiment, what we do is that there is an incoming photon, and that incoming photon, when that incoming photon collides with the target electron which we keep at rest, there is a shift in the wavelength of that incoming photon, and we wish to compute what is the change in that particular wavelength of the photon. So we assume that you have an incoming photon, you have an electron at rest, and that photon gets scattered at some angle phi, and the electron gets scattered at some angle theta. In this particular experiment, we wish to compute the change in the wavelength of the photon, because obviously when this photon basically collides with the electron, there will be some reduction in the amount of energy of that photon, because some of its energy will get converted into the kinetic energy of this electron. So obviously we know the relation between energy and the wavelength E is equal to hc over lambda. So basically some of its energy of the photon will get decreased. That will lead to the increase in the kinetic energy of the electron. So obviously the energy of that scattered photon will be less, or we can say that the wavelength of the scattered photon will be more. So we wish to compute that relation between the wavelengths of the incoming photon as well as the scattered photon, or basically I may say that we wish to compute the difference or the change in the wavelength of the incoming photon to that of the scattered photon. And we use since this is a collision, and we are very familiar with what we do in the collision. We basically use the conservation of linear momentum as well as the conservation of kinetic energy. We assume that this is an isolated system, so we can use those particular equations. Now, if you look at this, you have an incoming photon, and the energy of the incoming photon, we all know it's E is equal to h mu, and the linear momentum of that particular photon is h mu by c. This is a target electron at rest, so we assume that this electron is at rest, so there is no momentum of this particular electron. The momentum of this is 0. Now this is the scattered photon, and we are writing the energy of this scattered photon as E is equal to h mu prime. Obviously mu prime, because the frequency of the incoming photon will not be equal to the frequency of the obviously, because the energy would be different. I just explained that the energy of the incoming photon and energy of the scattered photon won't be the same, because obviously the energy of incoming photon will be more than the energy of the scattered photon, and so is the linear momentum of the scattered photon, which P is equal to basically E over C. We all know it. So P is equal to E, which is h mu prime over C. Now the energy of the scattered electron, we are writing this as E is equal to under root m square c raised to the power 4 plus p square c square. This is a very familiar equation. It's the expression for our relativistic energy, and we are assuming some momentum of the electron P is equal to P. We are not writing the exact expression, as we don't need the exact expression for the linear momentum of the scattered electron. We are just assuming that momentum to be P is equal to P. Now we will use our basic knowledge of collision, and we will basically write the conservation of momentum. We'll get some equation, we'll write the conservation of energy, we'll get another equation, and then we'll do some algebra to find out what is basically the shift in the wavelength of the incoming photon with that of the scattered photon. Now I have basically resolved this linear momentum along this, because the angles are involved here, the phi and here the theta. So when we would be writing the a linear momentum in the x direction, we'll use the conservation of linear momentum in the x direction and in the y direction. So obviously the components of the linear momentum would be involved, because as we know that linear momentum is a vector. We won't write such components for the energy because energy is a scalar. But of course the conservation of energy would also hold here. So if you see that this is the linear momentum of the scattered photon. So this vector that you can see is h mu prime over c. So obviously the x component of that would be h mu prime by c of cos of, this would be cos of phi. This would be cos of, this would obviously be cos of phi. And this will be along the y-axis, this will be h mu prime by c sine of phi. Similarly, this is the vector p, the linear momentum of the scattered electron. So along x-axis it would be p cos theta, and along y-axis this will obviously be p sine theta. Now when we will write the conservation of linear momentum along the y-axis, we will obviously put a minus sign for this p sine theta, because the direction of p sine theta and the direction of this h mu prime by c sine phi both are opposite. But in the process of writing down the linear momentum conservation in the x-axis, both p cos theta and this h mu prime by c cos phi are in the same direction. So we just write down the conservation of linear momentum first along the x-axis and second along the y-axis. So obviously the conservation of linear momentum along x-axis will be, along x-axis we have h mu by c. This is the linear momentum of the incoming photon, plus 0, because the linear momentum of the electron is 0, because initially that is along x. This is the momentum along the x-axis before collision. Now obviously after collision the linear momentum will be h mu prime by c cos of phi plus p cos theta. Yeah, this is the linear momentum along the x-axis of the scattered photon, and this is the linear momentum of the scattered electron. Yeah, that we talked about, p cos theta here and h mu prime by c cos phi here. Let's call this equation 1. Obviously, what happens along the y-axis? Now, first thing is clear that there isn't any momentum before collision in the y direction, because you can obviously see the photon. If you see in this picture, the photon is obviously moving towards the x direction and the electron is at rest. So obviously there is no component of linear momentum of the photon or of the electron along the y-axis. So basically along the y-axis, the total linear momentum along the y-axis of the electron and the photon before the collision is 0. So we are writing LHS as 0, and along the right hand side we'll obviously be using h mu prime by c sine phi, and as I just discussed, we'll put a minus sign because the direction of p sine theta and the direction of this h mu prime by c sine phi are opposite. So we use minus p sine theta. This will obviously be equation 2. Now we sort of rearrange these equations. So we multiply this equation 1 by c and this equation 2 by c. So, and we rearrange. After rearranging, we get here pc cos theta equal to h mu minus h mu prime cos of theta. So basically we multiply this equation 1 by c, this will be pc cos theta, and c cancels, and we send this h mu prime cos phi here. So we have h mu minus h mu prime of cos of phi. This is not theta, this is phi. So let's call this equation number 3, and we multiply this equation here. So we get pc sine of theta. This is equal to h mu prime sine of phi. Because c and c cancels from here, we multiply this equation by c, so we have pc sine theta. Let's call this equation number 4. Now what we do is, you see that we have pc cos theta, we have pc sine theta. You must have understood that we are going to square these terms and then we are going to add these terms. So what we are doing is, we are squaring equation number 3 and then we are squaring equation number 4 and we are adding this particular equation. So what we get is, we get p square c square. Obviously we'll get h mu whole square, and you must have understood that when we'll square this term, you have h mu square and then you'll have h mu prime cos phi whole square, and from this you get h mu prime sin phi whole square. So we get h mu prime whole square along with sin square phi plus cos square phi, and you'll also get a minus 2ab term from here. So we will have 2 h mu prime of cos of phi. So we have p square c square equal to h mu square plus h mu prime square, and sin square phi plus cos square phi is obviously 1, and we'll get minus 2 times h mu, only h mu prime and cos phi. Yeah, so this is what we get. Now let's call this equation number star. Now we know that what is the total energy of the scattered electron. Yeah, or no, let's say what is the total energy of the electron. Now you know the total energy, we can write this total energy, we can derive this equation particularly, and also it's a basic common sense that the total energy can be written as the sum of the kinetic energy plus mc square. Yeah, mc square is the rest mass energy and this is the kinetic energy, because you must have basically understand that what is the energy, what is the total energy. So energy can be written as the sum of the rest mass energy plus, if that object is moving, so we can add the kinetic energy to it and we get the total energy. Also we can write energy as under root p square c square plus m square c raised to the power 4. This is a very important expression. We'll derive this relation in some other video, but I assume here that you know this expression. It's a very famous equation, and everybody must know this. So we call this equation number 5 and we call this equation number 6. I hope you understand the logic of equation number 5, that its E is the total energy, and that total energy can be written as the sum of the kinetic energy plus its rest mass energy, and this is a very famous equation. You know, we can basically derive the relation between energy and momentum. You know what is the relation between energy and momentum for a photon? It's E is equal to Pc, and we can derive that equation, that result from here. We know that mass of the photon is 0, and if you put m is equal to 0 here, we get E is equal to under root p square c square. This term goes to 0, square the square root and the square cancels off, and we get E is equal to Pc. So this is a very famous equation, and everybody should know this particular equation. We'll of course derive this relation in some other lecture. Now what we do is we equate this equation number 5 with this equation number 6, and we square it so as to remove this under root. So we get kinetic energy plus mc square, because we are squaring it to remove the square root. We have p square c square plus m square c raised to the power 4. Now we can basically open this square root, we can basically open this square, so we get kinetic energy whole square plus mc square whole square plus 2 times kinetic energy mc square is equal to p square c square plus m square c raised to the power 4. Obviously this term and this term cancels off, so we get p square c square equal to this term cancels off and we get p square. Yeah, we get p square c square equal to kinetic energy. I was just checking the expression. Kinetic energy square plus 2 times kinetic energy. And remember, when I am talking about this kinetic energy is the kinetic energy of the electron, of the scattered electron. Now we think about this kinetic energy of the electron, and we are basically thinking about that what could be the possible value of this kinetic energy of scattered electron. You can pause this video to think about what is the kinetic energy of this particular scattered electron. Now if you think about it, and if you go back a few frames, when I was introducing you about the Compton effect, I told you that what is the source of this kinetic energy of electron. I told you that whenever the incoming photon basically strikes the electron, the incoming photon obviously loses some energy. So where does that particular energy go? That particular energy goes into the kinetic energy of the scattered electron. So there is the source of the kinetic energy of the scattered electron. So what is the kinetic energy of the scattered electron? That is basically the energy of the incoming radiation minus the energy of the scattered radiation, because that difference in the energy is what is the kinetic energy of the scattered electron. Because it is very obvious. You have a photon with some particular energy, that photon strikes the electron and it goes off with some another energy, and that energy is obviously less than the energy of the incoming radiation, or the not radiation, incoming energy of the incoming photon. So that difference in the energy is that particular value of kinetic energy of the scattered electron, and this is h mu minus h mu prime. If you take h common, you have mu minus mu prime. And now we substitute this value of kinetic energy of scattered electron in this particular equation. What we get is, we get p square c square is equal to kinetic energy, and we are squaring this particular term. What you get is, you get this whole square, okay, yeah, we just check if there is something wrong. No, we get, if we square this, we get h mu whole square minus 2 h mu prime plus h mu prime whole square. So we are basically squaring this particular equation. If we square this kinetic energy, we get obviously h square and mu minus mu prime whole square. We open this, we get mu square plus mu prime square minus 2 mu prime, and we multiply this h square with the every term. So we basically get this expression. If we put the value of kinetic energy here, we simply get plus 2 times you have mc square, and you put the value, you get basically h mu minus h mu prime. This is the value of d square c square. Now you know from equation star above, if you look at this equation star, we have already derived the relation of this p square c square. Now what is this p square is? Let's substitute the value of this p square c square from star and we equate this to here. What we get? We get, just a second, we get, you have h mu whole square minus 2 h mu prime. I am just writing the value of p square c square from the equation number star, h mu prime whole square, and now this is equal to this above result, which is h mu whole square minus 2 times h mu prime, this h mu prime square plus 2 mc square, and this is h mu minus h mu prime. Now a lot of things would have got cancelled, so this h mu square, h mu prime square, and we can now, if you look at this equation carefully, we can just bring this minus 2 h mu prime minus 2 h mu prime to that inside. This is and we can write the equation of this 2 mc square, this particular value, to be equal to this. So we get 2 mc square, if you look at this carefully, h mu minus h mu prime. If we bring this minus 2 that side, what we get is, we get 2 h mu prime times 1 minus of cos theta. This is what we get. Now if we divide this particular equation by 2h square c square both sides, what we get? We get the c square, so divide above equation by 2h square c square. If we divide it, we get the c square and c square goes off, 2 goes off, we have m over h square, this is h, and this is h mu minus h mu prime. This is equal to 2 and 2 cancels, this h square and this h and h square cancels off. You have mu prime over c times c. This is c square. I am writing this as c times t, c times c. The reason you'll get very soon, and this is 1 minus cos of theta. Okay. Or is it cos of phi? Wait, let me just check. I am writing this theta. It's my bad. I'm not sure. I have brought this expression. Yeah. Okay. I'm very sorry. It is cos of phi here. I'm using theta, but it is phi. I'm very sorry. This is phi. This is phi. Yeah. Now this is the equation that we got. Now we wish to write this equation because at the start I have told you that we are basically interested in calculating what is the shift in the wavelength of the incoming photon to that of the scattered photon. We want to actually calculate the difference in the wavelength of the incoming photon with that of the scattered photon. So, and we are seeing this mu and mu prime here. So we basically wish to convert this mu in terms of lambda. We want to convert this expression in terms of lambda. So what we do? We basically, okay, so we don't have a c term here. So what we can do? Okay, so first thing first, Also you can see this H cancels with one H, and I am multiplying this left hand side by C. You see this H, obviously this H and H cancels off, so one H remains. I am writing C here, and this is, yeah, or no, I am writing it like this. I am multiplying C here, it's H here, and I am writing mu over C minus mu prime over C. Okay, so I have multiplied this C here, and I am dividing by the C here, and this side remains same. This is mu over C, this is mu prime over C, and this is 1 minus cos of phi. Yeah. Now we know the relation between the frequency and lambda with the speed of light. We know that mu over C is lambda, 1 over lambda. We know this expression that mu by C is 1 by lambda. So obviously this mu prime over C will be 1 over lambda prime. This is basic. So what this expression becomes? This expression becomes MC over H, and this mu by C I am writing 1 by lambda. This is 1 over lambda prime, and this is equal to mu prime, or I should basically write this expression too in the form of lambda, or let it be. I'm writing it like this. I should write. So this mu by C becomes 1 over lambda, and this mu prime by C becomes 1 over lambda prime, and this is 1 minus cos of phi. Now if you take this LCM, you get MC over H, you have lambda prime minus lambda over lambda prime. This is equal to 1 minus cos of phi over lambda prime. This and this cancels off. You get lambda, you get lambda minus lambda prime as H over MC times 1 minus cos phi. So this is the expression of change in wavelength that you get. Yeah. Or whether it should be lambda prime minus lambda, I'm not sure, because if you see the energy of the incoming of the outgoing photon will be less. Yeah, if the energy of the outgoing photon will be less, yeah, so lambda will be more. So obviously this will not be lambda minus, this will be lambda prime minus lambda. The shift in the wavelength. So this is the particular shift in the wavelength. So we can write this is this particular, we call this shift as delta lambda. This is H over MC times 1 minus cos of phi. So this is the final expression for the shift in the wavelength, where this H over MC is a constant, and this we call this H over MC as the Compton wavelength. And what is this angle phi? Go back to the diagram. This angle phi, if you look carefully, this angle phi is the angle with which the photon gets scattered. So we have to remember this, that this phi is the angle with which the photon is scattered. And this H over MC is a constant. You know that H is a constant, this M is the mass of the electron, this is a constant, and this C is the speed of the light. This H over MC, we call it the Compton wavelength. And its value is close to 2.42 picometer. You know picometer, 10 raised to the power minus 12. So this is the value of the Compton wavelength. Now, if I ask you a very fundamental question. So first let us write this wavelength, that shift in the wavelength in terms of this Compton wavelength. So this is obviously lambda c. We denote it by lambda c. So this lambda c times 1 minus cos phi. Now you know what is this angle phi. This angle phi is the angle between the our normal the x-axis and the angle of the angle by which the photon gets scattered. Now I am asking, when will this change in wavelength, that is delta lambda, will be maximum? So this delta lambda will be maximum if the value of this phi is 180 degree, because obviously when this value of phi will be 180 degree, its value will be -1, and this will be 1 minus of -1, and that will be 2 times value of the Compton wavelength. So we can also write this important result, that the shift in the wavelength, this delta lambda, will be maximum when phi is equal to 180 degree, because when this phi is 180, cos phi becomes -1, and obviously this delta lambda becomes 2 times lambda of c, which we can calculate by multiplying 2. So this will be equal to 4.84 picometer. So this is when the phi is 180 degree, means that you basically projected that photon towards that electron, and phi is equal to 180 means that the incoming photon backscattered. So basically it scattered back towards the direction with which it came. So that is the place at which this delta lambda will be maximum. And when what is the value of phi for which that change in the wavelength will be 0? So basically 1 minus 1 is 0. So basically you can say the value of delta lambda will be minimum. Let's write it down. Will be minimum when phi is 0, because when phi is 0, cos 0, what is the value of cos 0? Cos 0 is basically 1, and this 1 minus 1 is 0. In that case, your delta lambda will be 0. This is the change in the wavelength. This is maximum change, and this is the minimum change when we are putting phi is equal to 0, cos 0 is 1, and you get change in the wavelength that as delta lambda is equal to 0. So this is basically what I wanted to explain in the Compton wavelength. As I just discussed, that Compton wavelength was a very, very important experiment. In this, you can see from the above equations, in this particular derivations, we have only used the basic conservation of momentum and the basic conservation of energy, and we get the change in the wavelength. It is very, very important from the exam's point of view, because they can just ask you what is the change in the wavelength. They'll give you some particular value of phi. They may even say that what is the value of the change in wavelength when the photon gets backscattered. So you must remember that when the photon gets backscattered, this phi is equal to 180, cos phi is -1, and you get the maximum change in the wavelength, that is delta lambda is equal to 2 times lambda c. And when the phi is 0, that is when the incoming photon gets straight along to the x-axis, that is the scattered photon does not get deflect. That is the time when this change in wavelength will be 0, it will be minimum. So this is what I wanted to explain about the Compton effect. Thank you.